you build something incredible. A quantum algorithm that helps real machines solve problems classical computers can barely touch. Suddenly, complex equations turn into cleaner energy models, faster drug discoveries, better traffic systems, and yes, even faster, smarter artificial intelligence, because quantum computing could speed up machine learning, optimize neural networks, and process massive data sets that would take classical computers days or weeks. But would this life-changing tech be protected under intellectual property? Would it be freely available or shared among experts to build something better together? Today on Intangiblia, we explore how quantum computing is moving from the lab to real life and how the future is being shaped one qubit at a time.
You are listening to Intangiblia, the podcast of Intangible Law, plain talk about intellectual property. Please welcome your host, Leticia Caminero.
Hello, and welcome back to Intangiblia, where we decode the invisible laws behind the world's most powerful ideas. I'm Leticia Caminero, your host. Today's episode takes us to the edge of innovation, where science fiction is becoming science fact. We're talking about quantum computing, not just theory, not just hype, but real technology already reshaping how we approach security, medicine, energy, and even artificial intelligence.
And I'm Artemisa, your positively entangled AI co-host. I promise to keep the jokes superpositioned and the facts spin aligned. If anything collapses into confusion, just blame quantum decoherence.
We're talking about simulating quantum systems to accelerate drug discovery, like identifying new compounds for Alzheimer's or antibiotic-resistant bacteria faster than ever imagined. Solving the electronic structure problem to design next-generation batteries such as lithium-air and solid-state batteries, promising ultra-high energy density and near-continuous power for electric vehicles, satellites, and remote infrastructures.
Performing high-accuracy molecular dynamics to predict protein folding for life-saving treatments, as in DeepMind's AlphaFold models now being explored through quantum-accelerated refinement, modeling climate and fluid dynamics to improve long-range forecasting, supporting global systems like Copernicus and NOAA in predicting extreme weather events with atomic-level precision,
optimizing combinatorial problems for use in real-time traffic routing, think FedEx or Uber Freight, smart energy grid management, and financial portfolio optimization, like JP Morgan's work on quantum Monte Carlo simulations. Enabling quantum secure communication through quantum key distribution systems already deployed in Chinese misuse satellite and Europe's Quantum Internet Alliance.
running quantum-enhanced machine learning for drug target identification, fraud detection, and large-scale data classification, powering platforms like Xanadu's Penny Lane and IBM's Qiskit, and tackling cryptographic challenges such as factoring large primes or simulating quantum-resistant algorithms, pressuring security systems worldwide to prepare for post-quantum encryption standards.
And at the intersection of all of this sits artificial intelligence. Quantum computing could dramatically accelerate AI by optimizing deep learning models, reducing training times for massive datasets, and enabling entirely new architectures like quantum neural networks. AI systems that today take days to train might soon evolve in hours with greater accuracy, fewer researches, and exponentially more potential.
Quantum computing isn't just a concept, it's already being engineered into tools targeting some of the most complex and critical computational challenges humanity faces, including the future of intelligence itself.
And where there's powerful tech, there's intellectual property. If quantum computers can solve problems classical ones can't, who owns the breakthroughs? Can you patent something built on probability? And how do legal systems built for nuts and bolts handle machines that don't always follow classical logic?
That's what we're exploring today, the legal puzzles, the case law that's changing the game, and the bold ideas shaping how IP might evolve in a quantum-powered future.
Before we jump in, a quick reminder, Artemis and I, while delightful and unusually persuasive, are powered by artificial intelligence. Any legal opinions we offer are purely for educational fun, not legal advice. All right, let's break it down. What exactly is quantum computing and why is everyone suddenly obsessed with it? Let's start with the basics. Classical computers, like the one you're using to listen to this podcast, process information using bits, zeros, and ones. Every app, every photo, every emoji is just a long sequence of those two numbers. Everything runs in a straight line, yes or no, on or off. But quantum computers use something completely different, qubits. And qubits don't like to pick sides. Thanks to a strange little rule of quantum physics called superposition, a qubit can be a zero and a one at the same time. It's like trying to flip a coin and have it land on both heads and tails until you look.
Or better yet, imagine Schrodinger's cat, classic quantum thought experiment. You put a cat in a box, no animals harmed, we promise, and rig it so there's a 50-50 chance it's either alive or not based on a quantum event. Now, here's the weird part. Until you open the box, the cat isn't just one or the other. In quantum theory, it's in a superposition, both alive and not at the same time. Only when you look do you collapse the state and force the universe to decide.
In a quantum computer, that same idea applies to data. A qubit holds multiple possibilities at once. And when you run a quantum algorithm, it doesn't test each option one at a time like a classical machine. It explores many paths simultaneously. And then when you measure the result, you get the best answer based on all those probabilities.
And that's what makes quantum computing powerful. It's not just faster, it's fundamentally different, like switching from a bicycle to teleportation.
This unlocks wild possibilities. Quantum machines could simulate molecules for drug discovery, model the climate with atomic precision, or optimize entire power grids in seconds.
Even your local pizza delivery route could get a quantum upgrade. Imagine always getting the fastest delivery, even during a storm on a Friday in rush hour. That's the dream.
But here's the legal twist. Quantum computers don't just challenge physics, they challenge the law. Because when someone invents a quantum algorithm, a new quantum device, or a way to fix noisy quantum data, how do we protect that invention? Can it be patented like a toaster? Or is it more like an abstract idea, something you can't own? Today's quantum computers are still a little messy. They are powerful, but also prone to errors. The term for this is noisy. That means the results you get from quantum calculations can be unstable, inconsistent, or just plain wrong if you don't clean them up. This noise isn't someone sneezing in the lab. It's tiny environmental factors like temperature fluctuations or electromagnetic interference that disrupt the fragile state of the qubits. Making a quantum machine useful means building algorithms that can work with or even correct for that noise.
And that's where a lot of innovation is happening right now. Some of the most valuable work in quantum computing isn't flashy. It's about making today's imperfect quantum machines actually usable. And the people solving that, they want to protect their methods. These innovations are challenging to describe it in a way a patent examiner can fully understand. Some of this tech is so new that we don't even have the vocabulary for it yet.
That's where intellectual property comes in. Our current IP systems, especially patents, were built for inventions that are physical, mechanical, maybe digital, but logical and observable. Quantum computing, on the other hand, operates in probabilities, entanglement, and other phenomena that don't always fit neatly into a traditional patent form.
So today, researchers and startups around the world are asking the same question. If I create something revolutionary in quantum tech, will the law recognize it? Will I be able to protect it? Or will I be stuck watching someone else copy it just because the system can't keep up?
The stakes are high. This isn't just about who gets credit, it's about who gets funding, who gets access, and how innovation is shared or controlled on a global scale. That's why we need to understand not just what quantum computing is, but how the legal world is or isn't keeping up with it. And in our next segment, we dive into a case that could shift how quantum inventions are treated by patent offices around the world. Let's move from theory to reality with a case that's already making waves in the quantum patent world. Ex Parte Gao decided by the US Patent Trial and Appeal Board in 2025. If you've never heard of it, don't worry, this case isn't famous yet, but its implications, they're huge. Here's what happened. Dr. Yudong Cao, a quantum scientist and entrepreneur, developed a hybrid quantum classical algorithm. The goal? To solve large systems of linear equations efficiently, even on the noisy quantum computers we just talked about.
This isn't the kind of dreamy future quantum machine that works flawlessly. In theory, this was for today's imperfect, limited, glitch-prone devices, and his algorithm helped make them useful. So naturally, he filed for a patent.
But then came the wall. The USPTO examiner rejected the application. Why? Because according to the examiner, the invention was just a mathematical concept, a set of equations without a specific tangible application. And under US patent law, abstract ideas like math formulas are not patentable. Specifically, the examiner cited 35 USC S181, the part of US law that defines what kinds of things can be patented. Thanks to a famous Supreme Court case called Alice Court called Elas Bank 2014, patent applications that rely on abstract ideas like math or general algorithms are often struck down unless they clearly show a significantly more technical application.
And let me tell you, Alice has been the heartbreak of software inventors for a decade. So many creative technical solutions have been rejected because they're seen as just code or theory.
But in Dr. Zhao's case, he appealed. And here's where things got interesting. In early 2025, the Patent Trial and Appeal Board reversed the examiner's decision. That's right, the same patent office said, actually, this does qualify as a real patentable invention. Why? Because Dr. Zhao's algorithm didn't just describe math on a page, it was specifically designed to work on a quantum machine. The patent claims included steps like preparing a quantum state, applying quantum gates, and using quantum measurement to produce a real-world result.
In other words, the board said this wasn't abstract, it was practical. It turned noisy quantum machines into useful problem solvers. That's not just theory. That's tech.
The board even said that these steps integrate the recited abstract idea into a practical application. That's a magic phrase. It meant the invention wasn't just math, it was a technical solution to a technical problem. And that's a huge deal.
Because up until now, most quantum algorithm applications got lumped into the same bin as software math. Too abstract, try again later. This case carved out a path. If your quantum method is tied to hardware and solves a real limitation, it just might be patentable.
Let's zoom out for a second. This is a US case and it's not binding precedent, but it's a signal. It shows that the system may be starting to adapt. Patent examiners and courts are slowly realizing that quantum computing doesn't fit neatly into classical boxes.
The case also shows something else. How you write your patent matters. Dr. Zhao's application didn't just say, here's a clever algorithm. It walked through the quantum steps. It framed the invention as solving a technical challenge. It gave the board something solid to work with.
That's a lesson for every quantum inventor out there. Don't hide behind math. Show the machine. Describe the problem. Explain the fix.
And a side note for the legal nerds, this case didn't just tackle subject matter eligibility. It also brushed up against written description requirements, whether the patent explained enough detail for a skilled person to replicate the invention. Spoiler, it passed that too.
So to sum it up, Ex Parte Gao was the first real sign that quantum algorithms, when tied to hardware and technical outcomes, can clear the US patent hurdle. That doesn't mean it's easy. but it means it's possible.
And in the world of quantum law, possible is practically revolutionary.
Intangiblia, the podcast of intangible law, plain talk about intellectual property.
So Ex Parte Gao showed us what's possible when quantum meets the US patent system. But what about the rest of the world? Let's take a look at how other countries are approaching quantum innovation and intellectual property.
First stop, Europe. The European Patent Office hasn't had a headline-making court case yet, but it's quietly shaping the rules for quantum inventions through its official examination guidelines. The EPO allows patents for quantum technologies, especially if the invention solves a clear technical problem. So if you're designing a quantum sensor, a control system for stabilizing qubits, or a quantum-enhanced encryption device, and you frame it as a technical solution, Europe's doors are open.
A great example, Swiss company ID Quantique, known for quantum cryptography. They've successfully patented several secure communication technologies across Europe by grounding every claim in physical implementation.
Now let's talk about China, a key global leader in the development of quantum technology. Over the past few years, China has made remarkable progress, both in scientific discovery and patent activity. Companies like Alibaba, Baidu, and government-submitted institutions such as the Chinese Academy of Sciences are conducting world-class research and filing patents across a wide spectrum, from superconducting qubits to quantum cloud platforms.
And China isn't just filing, they're innovating. In fact, China has become one of the top jurisdictions for quantum communication and quantum sensing patents, with internationally recognized achievements like the MISU satellite for secure quantum key distribution. Patent protection has been an important part of that ecosystem. The China National Intellectual Property Administration, CNIPA, has granted many of these applications, and examiners have been developing the capacity to evaluate highly technical emerging technologies.
While no major court cases have publicly tested these patents yet, the infrastructure is in place. China has clearly recognized that protecting intellectual property plays a critical role in supporting high-tech entrepreneurship and long-term research investment.
And that matters not just for China, but for the global community, because when more countries contribute to the quantum ecosystem, we all move forward.
Let's head to India, where Section 3K of the Patent Act has traditionally excluded mathematical methods and software per se. That includes quantum algorithms unless they produce a technical effect. But in 2019, the Farid-Alani case opened the door a little wider. The Delhi High Court acknowledged that software and by extension, quantum computing could be patentable if it leads to a technical advancement.
Indian innovators have since begun framing quantum inventions in ways that highlight their practical, technical contributions. While it's still a challenging environment, there is growing momentum to modernize IP laws in step with emerging technologies.
In Japan, the government has prioritized quantum technologies as part of its national innovation strategy. Major players like NTT and Toshiba are actively developing quantum hardware and communication systems. The Japan Patent Office, JPO, has issued patents related to quantum cryptography, qubit design, and noise-resilient quantum circuits. To support this, the JPO has provided updated guidance to examiners on evaluating computer-implemented inventions, especially those tied to real-world technical effects, which is key for quantum claims.
Canada, home to D-Wave and the University of Waterloo's Quantum Research Hub, has positioned itself as a leader in quantum commercialization. The Canadian Intellectual Property Office, CIPO, allows patents for software and algorithmic inventions if they are part of a practical application. As a result, Canadian inventors have successfully patented quantum annealing systems, control methods, and hybrid algorithms. Canada's National Quantum Strategy, launched in 2023, explicitly includes IP protection as part of its commercialization track, encouraging inventors to secure rights early and internationally.
And in Australia, the government has funded quantum research through the Australian Research Council and created dedicated programs like the Center for Quantum Computation and Communication Technology. The IP Australia office follows a principle similar to Europe's. A software invention, including quantum algorithms, can be patented if it produces a technical effect. Examiners there have granted patents for photonic chip designs, error-correcting code systems, and quantum random number generators. Australia has also introduced examiner training modules on emerging technologies to keep pace with developments in quantum and AI.
And let's not forget countries that are steadily expanding their presence in this space. Brazil, for instance, has seen growing investment in quantum research through public universities and national innovation programs. Institutions like the University of Sao Paulo and the National Institute for Space Research are conducting work on quantum optics and quantum communication. While Brazil's patent law excludes software per se, inventors are working within the system to patent quantum sensors, encryption devices, and hybrid technologies that involve hardware-software integration.
In South Africa, government funding through the National Research Foundation is supporting quantum photonics research, especially in partnership with universities like Stellenbosch and Wits. South African patent law allows protection for inventions with a technical effect, so there's room for applied quantum systems, though we're still waiting on the first wave of high-profile filings.
Kenya and Nigeria are both part of the African Regional Intellectual Property Organization, or ARIPO, which has begun examining how member states can align their patent examination practices with global developments in emerging technologies, including quantum computing. While local quantum computing R&D is in the early stages, these countries are engaging in policy dialogues, tech transfer planning, and capacity building programs to ensure they are not left behind.
And that's key. The goal isn't just to react later, it's to build the legal and institutional readiness now so that as quantum research expands globally, IP frameworks in Latin America and Africa are ready to support innovators and attract investment.
Now that we've seen the legal signals and early decisions around the world, let's talk about where things actually stand right now. How are current IP systems treating quantum computing inventions? And what are inventors, startups, and research institutions doing to protect their work?
Let's start with what's easiest to protect: quantum hardware. You build a new kind of chip, a better cooling system, or a more stable qubit design, patent offices will generally welcome you with open arms. These are physical, measurable, clearly technical inventions. Think superconducting circuits, ion traps, dilution refrigerators. If it fits in a lab and you can draw it, there's a strong chance it's patentable.
But what about the software, the algorithms, the protocols? That's where it gets trickier because in many jurisdictions, including the US, software that looks too much like math is still treated as an abstract idea, which means it's not eligible for a patent unless you can show a clear technical improvement.
Remember the Alice Core v. LS Bank test we mentioned earlier? That case still looms large. It asks, 1, is the invention directed to an abstract idea? 2, if yes, does it include something significantly more, like a technical implementation? In quantum computing, the answer often depends on how the application is written.
And that's where strategy comes in. Inventors are learning how to frame their quantum innovations to highlight technical contributions. Let's say you develop a quantum algorithm for solving logistics problems. If you just describe it as a mathematical optimization, you'll probably get rejected. But if you show that your method specifically improves the functioning of a quantum device, for example, by compensating for noise, reducing the coherence, or enabling faster conversions, you're in a much better position.
Patent examiners aren't just looking at what you invented. They're asking, does this invention improve how a computer or a quantum system actually works? If yes, that's your golden ticket.
That's why we're seeing more hybrid claims, blending hardware steps with algorithmic logic. For example, instead of just saying, this algorithm solves a matrix, a patent claim might say, a method comprising preparing a quantum state on a superconducting qubit device, applying a sequence of quantum gates corresponding to matrix operations, measuring the resulting quantum state, and outputting the classical approximation of the solution vector. In that structure, you're not just describing math, you're showing how it's executed on actual hardware step by step to produce a technical result.
And that's what makes all the difference. It ties your invention to the real world, to a device, to a process, to a use, not just math floating in space.
Is the legal equivalent of saying, this isn't just an idea. I build the thing, I run the thing, and here's what it does. And it's working. We're seeing more patents granted when inventors go the extra mile to explain how their quantum algorithm isn't just clever, it's practically useful.
So whether you're designing error correction software, hybrid solvers, or real-time control systems, framing your innovation as a technical improvement, especially one that plays well with noisy quantum hardware, is your best bet. Now let's talk about what happens after you've secured protection or figured out which parts to keep secret. Because the next big question is, how do you use that IP?
For many quantum startups and research institutions, the answer is licensing. Let's say you're a lab that developed a quantum control system, but you're not planning to commercialize a full machine. You can license your patent to a hardware manufacturer or quantum cloud provider. They get to use the tech. You get royalties or a partnership deal. Everybody wins.
And this is where it gets really interesting. Quantum IP isn't just about owning, it's about sharing strategically. Some companies are forming cross-licensing agreements, especially in areas like error correction, where different groups are solving similar problems. It helps reduce litigation risk and encourages collaboration.
There's also talk of creating quantum patent pools in the future. That's when multiple organizations agree to license certain patents to each other or to third parties under fair, reasonable, and non-discriminatory terms. It's a model we've seen before in telecom and video compression. And with quantum technologies converging fast, some experts think this kind of structure could help avoid costly legal battles while accelerating innovation.
But right now, it's still early days. Everyone's building portfolios, testing claim strategies, and watching closely to see how examiners and courts respond.
Academic institutions are also playing a big role. Universities are filing more patents on quantum discoveries and spinning out companies to bring them to market. In many cases, tech transfer offices are learning how to tailor patent language for quantum specific claims.
And governments are catching on too. In places like Canada, Japan, Australia, and the EU, national quantum strategies now include IP support, grants that cover filing costs, patent training for researchers, and commercialization workshops for quantum entrepreneurs.
We're also seeing early capacity building efforts in countries like Brazil, South Africa, and Kenya, making sure examiners, inventors, and policymakers are all learning together. Because this isn't just about patents, it's about shaping entire ecosystems that can sustain quantum innovation and make it accessible.
Which brings us to the heart of it. Intellectual property isn't just a legal tool, it's a strategic language. The better we learn to speak it in the quantum context, the more powerfully we can share, protect, and build on these world-changing ideas.
All right, before we decohere completely, let's bring this all back together. Here are 5 takeaways from today's journey through quantum computing and intellectual property.
1, quantum computing isn't just theoretical anymore. It's real, it's messy, and it's already solving problems classical computers can't. That matters for science, for society, and for law.
2, patenting quantum inventions is possible, but it depends heavily on how you frame your claim. Tie your algorithm to hardware, solve a technical problem, make it tangible.
Globally, IP offices are adapting at different speeds. Countries like China, the US, Europe, Japan, and Canada are leading with updated guidelines and big patent volumes. Others are preparing, learning, and watching closely.
before. Inventors are getting creative using hybrid claims, trade secrets, open source platforms, and international filing strategies to protect their work in a still shifting legal landscape.
5. The future of IP and quantum tech depends on clarity, training, inclusion, and a little imagination. If we modernize the system thoughtfully, we can build a future that's innovative, fair, and a little bit magical.
That's all for today's episode of Intangiblia. If you've ever doubted whether the law could keep up with the future, just remember, sometimes it needs a little push from the people building it.
And sometimes the future just needs a better patent attorney.
We'll be back soon with more untold stories where creativity, technology, and law collide.
Thanks for listening to Intangiblia. Stay brilliant, stay protected, and don't forget to collapse your wave function on the way out.
Thank you for listening to Intangiblia, the podcast of intangible law, plain talk about intellectual property. Did you like what we talked today? Please share with your network. Do you want to learn more about intellectual property? Subscribe now on your favorite podcast player. Follow us on Instagram, Facebook, LinkedIn, and Twitter. Visit our website www.intangiblia.com. Copyright Leticia Caminero 2020. All rights reserved. This podcast is provided for information purposes only.